Hello, welcome again. So far we've seen the convolutional layer. We talked about the different type of convolutions and so on. Talked about the nonlinearity layer. Talked about the sigmoid, the ReLU, and we talked also about the pooling layer. Example, the max pooling. Now we talk about the normalization layer. And this layer is useful when we're dealing mainly with the ReLU function. So if we use here a ReLU, because the values or the output of the ReLU are unbounded, so you have unbounded activities, so we need to control them. We need to normalize somehow. So we use this normalization approach. And then many types of normalization approaches have been proposed for using the ConvNet architectures. One of them is the local response normalization, which has been used for AlexNet that we're going to talk about later. And there are two approaches in this case, the inter-channel and the intra-channel LRN, and there are other approaches. But the thing is that these layers have fallen out of favor because their contribution has shown to be minimal, if any. So it was initially used, for example, for AlexNet, but then people realized that this normalization doesn't make any difference, so it's not popular anymore. So So I'm not going to go into the details of this, but if you want to learn more about it, you can go to this blog here, and then this author explains why it is used, why we use normalization, namely when we use these activation functions like the ReLU and so on, and then we want to bound our output with we want to bound our output so it doesn't go out of control. He talks about the local response normalization for the inter-channel and the intra-channels. And then an important observation is that this normalization layer is non-trainable, which means that you do not, when you do the back propagation to adjust your weights or to learn your filters, you do not, there are no parameters here that in the normalization layers which need to be learned. So it's purely an equation that you use. So for example, this is the value before normalization. This is the value after normalization. So you just divide this by a certain factor, and then the K here is used to avoid dividing by 0, and then it explains the different hyperparameters. So K avoids any singularities or division by 0. Alpha is used as a normalization constant, and the beta is a contrast constant. But anyway, we're not, so this is the one that has been used in AlexNet. We're not going to go into the details. And also that blog gives some examples showing the values before the normalization and after. Now, let's look at the loss function. So remember, when we have our input or data set, we feed it to the network, and then because it's supervised learning, so we have some desired outputs or some target outputs, and then we built a loss function. We've seen the L2 norm, L2 loss, where we minimize the sum of the square root difference between the desired output and the actual output that you get from the network. But there are other loss functions which have shown to perform better depending on the type of function of application, depending on the type of network that you use. So the loss function definition, it quantifies the difference. So before we called it error function when we looked at the multi-layer perceptron. Now in the case of the CNN, it's called the loss function. So it quantifies the difference between the estimated output or the actual output which is produced by the model, and the correct output or the desired output or the ground truth. And the type of loss function depends on the problem that you're trying to solve, whether it's binary classification, whether it's identification, whether it's multi-class classification, or whether it's regression, and so on. So we've seen that, for example, for the case of the binary classification, where we want to detect whether an object is present or not, we've seen that for the case of the multi-layer perceptron, and so on. So let's look now at the multi-class classification. And then before we do that, let me just give you an example, which borrowed the slides from this source. So we have, so the objective here is to classify. So we have a network, and we would like to give it images, and we would like to have some outputs, and we have 4 classes here. So class 1 is for cats, okay? Class 2 is for dogs. Class 3 is for chicks. And then class 0 is for all the other classes, in this case, koala and other animals as well. So we have at the output of our network, we're going to have 4 neurons, where this one will give you the probability of having a cat, given your image here, X, probability of having a dog given X, probability of chicks given X, and then probability of others, okay? And then you usually have a one-hot encoding, meaning that if it's a cat, you're supposed to have 0, 1, 0, 0. If it's a dog, you were supposed to have, or the desired output is supposed to be 0, 0, 1, 0, and so on. So it's one hot encoding. And yep, okay. So once you do your training, so we'll look at the softmax layer, which is usually used at the end of your network. So this layer has 4 neurons as well, or 4 outputs, and the activation here at this layer is given by the weights of this layer multiplied by the previous activation, which is coming from the previous nodes or neurons, plus the bias here. And the output is given by this activation function, which is called the softmax function, which is just exponential of this activation of whatever you got here. So for example, if the activation is given by 5, 2, minus 1, and 3, so your T would be given after you feed it to the activation function. It will be given by e to the power 5, e to the power 2, e to the power minus 1, e to the power 3. And then the output is given by this formula here. You just divide by the sum of the TIs. So these are if you calculate, use your calculator, you get these TIs. You sum them, you get 40, I think this should be 14, 7. Yeah, something. So you sum these TIs, and you're supposed to get 17.63. So you divide. So your output is going to be that TI divided by the 70, the one. Sorry. So this is 176.3. So you have 148.4 plus 7.4 plus 0 plus 20.1. So you get 176.3. So your output is going to be Ti, which is this number divided by the sum. And then, so this is e to the power 5 divided by 176.3. And then the second output is going to be E2 divided by the sum. And then E3 and so on. So here, your actual output is, so you take the highest probability. So you think that it is most likely that this is class 0, okay? Now, to train your neurons to adjust your weights and so on, you can use different loss functions. And then we said that one of them is the softmax loss, or also called the cross-entropy loss, which is defined by this formula. So remember, we got our outputs here. So this is the predicted, P for predicted output. So these are the numbers we got. And then this is the actual. So if it is class 1, so it's because we're using one hot encoding, so it's 1000. So we simply just compute these formulas by replacing the yn, which is 1, and this term here, we've already computed it before, actually. It's e to the power 5 divided by 176.3, and then we take the log of that. And then we do with the other training sample and so on. So assuming that we have n training sample. Just note that this cross entropy is not, so LPY is different from LYP, so you have to be careful when you do it, because here you're taking the log of the Pn, not the log of the Yn, so it's different. So this was the first loss function. Another loss function is the SVM Hinge Loss, which has shown to be popular or very important in the case of support vector machine. Hinge loss maximizes the margin between the true, the positive and the negative class samples using this loss function here. So it's just simply the max between 0 and this number. So if this number is negative, so it's 0, the loss is 0. If this number is positive, so it's this value here. And then the m is equal usually to 1. And the yn and the pn is the predicted and the yn is the desired or the actual one. And you do it for this number of n. So p is your prediction, y is the ground truth label, and n denotes the number of samples. And another last loss that we're going to see here is the Euclidean loss, which is also called the quadratic loss, the mean square error loss. And we defined it as the sum. So it's defined in terms of the squared error between, or the difference between the prediction and the ground truth, okay? And this is summed over all the samples. We're assuming that we have n samples, so we divide by n, and then the 2 is used for convenience, because when we take the derivative of this, it will cancel with, we've seen that for the case of the perceptron, the multi-layer perceptron. Okay, so far we've seen all the layers that we need to put together our network. So for example, this is the case of one of the networks called VGGNet. We're going to explain more about it later. So this one uses a 3x3 convolution kernels in all the layers, okay? And you can see here that this is an example where you have an image, a 224 by 224 image. So we have 3 channels, red, green, and blue. And then we use our filters, 3x3 convolution kernels with a number of channels here. We get our convolution and the ReLU, and then there is a max pooling in red, and then again another convolution, max pooling, convolutions, max pooling, convolution, max pooling, and so on. And then here we have fully connected layers or networks with ReLU, okay? And then we have a softmax layer that we've seen just before. So we've seen the convolution, we've seen the activation functions that this network uses, the pooling approach. So they use, this one uses a max pooling, and then the softmax. And and so this is all that you need to learn to be able to put together a network. As we said before, normalization layer is not used except in the case of AlexNet. You can see here that because you're using a kernel, a 3x3 kernel, we're going to show or explain that the resolution of the channel is decreasing, divided by 2 every time after each layer. So 24, 112, 56, 28, 14, 7, and so on. And then the number of channel doubles every time. Okay, so that's for the, now we have the architecture. Let's say we put together an architecture. Now we want to train our network. And we know that we need to have a loss function, define a loss function, and we need to train it. So this process tunes the parameters or the weights or the parameters of the kernel such that the input space is correctly mapped to the output space. The current estimate of the output variables is matched with the desired output. So we use a loss function to compare the output with the desired output or the ground truth. The matching function serves as an objective function during the training, and it is usually called the loss function or the error function. We've seen that. CNN training process involves the optimization. So we have an optimization problem of the model parameters such that the loss is minimized. So we define our loss function, we try to minimize it so that we find the parameters of the network. The optimization of such nonlinear models is a hard task, but now there are tools which allow you to solve it very easily. For example, TensorFlow. So the gradient-based methods come as a natural choice. So the amount of parameter update is called the learning rate. So remember, the way you adapt your parameters, this is the new parameters, old parameters minus eta, which is the learning rate, times the delta. And this delta is the gradient of the loss function. And each iteration, which updates the parameters, your parameters, meaning the weights and the bias, or the values of the kernel, in the case of the CNN, using the complete training is called an epoch. So when you have a whole data set, you do it once, this is one epoch, and then you look at your loss, and then you do it another time, another epoch for the whole training set, and you keep repeating several times until convergence, until you get your global minima. So no need to try to devise your own optimization algorithm or so. So the current packages, TensorFlow, PyTorch, offer a range of them for you. So now when you do your gradient descent, there are different ways of doing it. So one is the batch gradient descent. So in this case, you compute the gradient on the entire training set for a number of epochs. So you do it, you take your training set, and then you compute the gradient using this entire data set, and then you do it for another epoch, and then take the whole entire data set, do it for the whole epoch, and that's what you get basically. This is where you want to converge to. So after one epoch, you move here. The whole training set, you take the whole training set, you move here. And then the whole training set, you move here, and so on. So it is guaranteed to converge to the global minimum for the case of convex problems. For the non-convex problem, it can still give you the local minima. It won't converge to the global minima. And also it is because in the case where you have a large training set, so if you use the whole training set in one epoch to train your network, it's too much for your computer. Another approach is to use the stochastic gradient descent. And in this case, you perform parameter update. You update your parameters of your CNN for each set of input and output present in the training set. So it's just like if your batch is one. So you do it for each training sample. So this is your stochastic gradient descent. First sample, second sample, third sample, and so on. Finish with one epoch, you do it for the second epoch, and so on, one by one. So conversion is much faster compared to the batch gradient descent, but then the convergence behavior is not stable. So instead what you do, so batch gradient has problems, stochastic gradient has problems, so you do the mini batch gradient descent. And in this case, what you do, you take your training set. So for example, you have 1,000 samples, you divide them into 10. So you have 10 mini batches. And then you take, for each epoch, you take the first batch, you update your parameters, take the second batch, you update your parameters, and then when you finish the 10 batches, that's one epoch, and then you do it for another epoch. So it's an improved form of stochastic gradient descent, better than this one, and it provides a decent trade-off between convergence efficiency and stability. So this is the mini batch. So batch one, batch two, and so on. And then so the good thing also about the mini batch is you can divide your batches across a number of CPUs or GPUs, and that would be much faster. So some demos here so if you go to this website here, they give you a number of data sets. So for example, this one is the MNIST data set, which is a data set with a number of digits. The CFAR, which has CFAR 10, which has 10 classes of different objects. And then you can see there the number of your hyperparameters for the network, the number of layers, the number of the size of your kernel, and so on. And then you can play with these hyperparameters and these parameters, and then you can see how the error function converges or is decreasing or non-decreasing, or so. You can watch it. You have a graph of that, and then also you see your results. So it's quite interesting. So you can find it on this set. Thank you.